This is going to be a quick video to run through some practice problems with tension and springs. These will match up with the content problems. So first, tension. A 10 kilogram ball is suspended from a string. So here's my string, here's my ball, and it's 10 kilograms. And a person might be holding it, or maybe it's suspended from the ceiling. So the forces on that ball, if I do a sum of the forces, like Newton's second law, sum of the forces, well, there's the tension upward and the weight downward. If I were to draw a quick free body diagram of that ball, it has weight, which I label as mg. You might label it as W for weight or Fg for the gravitational force. And it has a tension upward. A tension is a force in a string or a cable or a cord or anything like that. Okay, so that equals ma. But in this case, because it's just suspended there, that equals 0. So I get T minus mg equals 0. So T must equal mg. And that equals the mass, which is 10 kilograms, times gravitational acceleration, which is 9.8 meters per second squared. So 10 times 9.8 is 98 newtons. So the tension in the string is 98 newtons. So the next example, that was A. Example B, a 10 kilogram ball is suspended from a string, but it's accelerating upward. And so, somebody's holding this string and accelerating this ball upward. So if I do a free body diagram, I have mg downward, but since it's accelerating upward, I know that that upward force, the tension, is going to be much bigger, or at least bigger, than the gravitational force. So if I do a sum of the forces equation, forces acting on the ball, again, I get tension minus mg equals ma, and now this is not 0. So tension minus mg, well, let me go ahead and start filling in some values. So tension minus the mass of the ball times gravitational acceleration, mg, 9.8 meters per second squared, this should be kilograms, equals m, 10 kilograms, a. It is an upward acceleration. Upward means positive, so positive 2 meters per second squared. So the tension minus 98, 10 times 9.8, equals 20. Add 98 to both sides. And so the tension equals 98, and 10 would be 118 newtons. And now we'll do example C. A 10 kilogram ball is suspended from a string but accelerates downward. So now we have a downward acceleration. So that's negative 2 meters per second squared. Free body diagram, the tension upward is going to be smaller than the weight. The weight hasn't changed, but the tension is smaller than the weight. So we have a downward acceleration. Remember, the acceleration is always in the direction of the net force. So if I do a sum of the forces on the ball, I get tension upward minus mg equals ma, just like the last time. I'm going to go ahead and rearrange while I have variables. Mg plus ma. So I just move the mg to that side. So that's 10 kilograms times 9.8 meters per second squared plus 10 kilograms times negative 2 meters per second squared. So this is 98 minus 20 equals 78 newtons. That was example C. A 10 kilogram ball is pulled along a frictionless surface. So it's being moved this way. A frictionless surface to the right with an acceleration. So there's some force acting, pulling it this way, with an acceleration of 2 meters per second squared. Okay, so in this case, if I drew a free body diagram, it has weight, and it has a normal force, and they're equal and opposite. So the sum of the forces in the y direction is 0, and it's not interesting. But the sum of the forces in the x direction, well, the only force acting is the tension. There is no friction force. It says it's a frictionless surface, so the only force acting in the x direction is tension. that equals ma. And so that's going to be the mass, 10 kilograms, times that positive acceleration, 2 meters per second squared, equals 20 newtons. And now we'll do the E portion. E says a 10 kilogram ball is pulled along the surface, being pulled to the right by a string with an acceleration of 2 meters per second squared. But now there's a frictional force in this direction. I use lowercase f for my frictional force. And the coefficient of friction is 0.150. And remember, friction equals the coefficient of friction times the normal force. And the sum of the forces in the y says, if I draw a free body diagram, it's not accelerating, so the normal force and the gravitational force are equal. So the normal force minus mg equals ma, or 0. So the normal force must be equal to mg. In this case, the normal force is just equal to the weight, which is 10 kilograms times 9.8 meters per second squared, which is 98 newtons. So the frictional force is 0.15, the coefficient of friction, times the normal force, 98. So I'm going to grab a calculator because I can't do that one in my head. 98 times 0.15 is 14.7 newtons. So now, the sum of the forces in the x direction is that applied force, and I'm going to call this that FA, applied force to the right, minus the frictional force, and that equals ma, and that would be the x component of the acceleration. And so, this is actually tension. So tension minus F equals ma. So the tension is going to be the frictional force plus ma. And I've already calculated the frictional force is 14.7 newtons. And the mass is 10, and the acceleration is 2 again. And this is kilograms, and this is meters per second squared. And so that's 20. And 14.7 plus 20 is 34.7 newtons. 10 plus 10 would be 24, so 34 is the tension. So that covers all 5 of those examples. I would like to talk about springs now. Continuing with those practice problems in your course content. Calculate the force produced by a spring. Remember, the spring equation is the force of a spring is minus kx. Well, we usually forget the minus. That's just a direction thing because the force the spring exerts is opposite in the direction of the displacement. So that F and that X always have an opposite direction. And that's why there's a negative sign. So it's got a spring constant of 3.5, and it is stretched by pulling it 0.75 meters. So the force required for that is kx, 3.5 newtons per meter, times 0.75 meters. So 3.5 times 0.75 in my calculator says that that force is 2.625 newtons. And so that's taking this spring that would typically look like this and stretching it out a distance of 0.75 meters. And now we're going to compress it, and it did go to here, so we're going to compress it a distance of 0.25 meters. And how much force does it take to smush that spring up? So F equals kx again, and it's 3.5 newtons per meter, and the compression is 0.25 meters. The force produced by the spring, in this case, since we stretched it to the right, this force is to the left. The spring force will oppose what we're trying to do. And so when we compress it to the left, the spring force is going to be pushing back to the right. So 3.5 times 0.25 gives me a force of 0.875 newtons pushing back against me. If I have pushed it to the left, it's going to try to push back against that. It's a restoring force. Okay, so let's do another one. What is the spring constant if compressing a spring produces a force of 5 newtons? So if F equals kx, then K must be F over x. So if using a 5 Newton force compresses at 0.35 meters, then 5 divided by 0.35 is 14.29 newtons per meter is the spring constant. Okay, this one's a little more complicated. So we have a mass that is 7.5 kilograms, and it's being pulled to the right by a spring so that it accelerates. This block has an acceleration of 2 meters per second squared, frictionless surface, and it's 7.5 kilograms. So if I look at the sum of the forces on that, it's just that spring force, because that spring is pulling it to the right, there's no friction force to the left. And so the spring force is just going to be equal to MA, and that's going to be 7.5 kilograms times 2 meters per second squared, and 7.5 times 2 is 15 newtons. So now if I want the spring constant equals F over x, and the force that the spring exerts on the object is the same as the force that the object exerts on the spring. So 15 newtons is the stretchy force, the spring force, and the spring is stretched 0.3 meters, and so 15 divided by 0.3 equals 50 newtons per meter. And we'll work another one. How much will the spring be pulled, stretched, if the force is 25 newtons and the spring constant? Okay, so if F equals Kx, x would be equal to F over K. And so if I have a 25 Newton force and the spring constant is 1.5 newtons per meter, 25 divided by 1.5 equals 16.67 meters. 25 divided, I'm checking my math real quick. Yes. Okay. A spring with a K value of 4.5 pulls a 10 kilogram ball across a frictionless surface of spring, pulling on it. Acceleration is 3 meters per second squared, and the mass of the ball is 10 kilograms. So again, the sum of the forces, it's just the spring force that's pulling the ball, and so that equals MA. So that's 10 kilograms times 3 meters per second squared. That's a 30 Newton force. Sorry for that right there, 30 Newton force. So if I want the distance, F over K, and that's 30 newtons divided by, the K value is 4.5 newtons per meter. 30 divided by 4.5 equals 6.67 meters. All right, and that is the end of this presentation. I hope you found it helpful.